A certain person in this crowd said I was crazy to try this, and I think he might be right, but we'll give it our best shot. A long time ago, probably 30 years ago, there was a fellow named George Lawrence who used to come to the skeptics meetings. And George came up to me one day and he said, Randy, he says, he went to a concert that night and he said, Randy, he said, something struck me last night. He said, you know, really all human beings do is process information. They don't do, I mean, what else do they do? And I thought, well, that's nice, George. Okay, it's like plastics, in the movie. And one of the things was that I'd learned information theory, and for me it was just an engineering thing, and I want to start out just, silly. So one thing is, Claude Shannon is the guy who came up with information theory. And Shannon, when he was doing his research, realized that any groups of ones and zeros could describe any numerical relationship, which was kind of amazing. It's basically saying you can describe anything with ones and zeros. Now, in typical engineering fashion, you think about this as engineering. You don't think about it as anything deeper than trying to solve a problem. And what he wanted to solve was how many conversations could you put at the same time over telephone lines? What is the information limit? Can you put everybody in the world through one pair of wires or what? Very much an engineering question. And information at its most basic level is a 1 or a 0, essentially a yes or a no. I mean, we use yes and no an awful lot. Now, each yes or no is a bit of information. In the game of 20 questions, you say, okay, there's going to be some famous person, and you get 20 questions to figure out who it is. And most of the time you're able to do that, which is kind of amazing. And Rudy Rucker did this great calculation, pointed out there's about 1 million famous people around, and 2 to the 20th is about 1 million. So you've got a pretty good shot just by yes or no questions of hitting that person. Normal written English, when Shannon did his research, shows that we have about 9.14 bits of information for each word of English. And keep that in mind, about 9, not just a little under 10 bits of information. Now, information content is about surprise. It's about, it can be made up of English words, but it's a far more general concept. I mean, English words is just one specific example. Information is the amount of surprise. A message can be, or information can be a picture, a sculpture, words, animal sounds, surface roughness, anything. And the letter Z contains more information than the letter E. Now, the thing is how is this? Well, here is a chart over here, and if you look at the bottom, you'll see very few words have Z in them. Very few. I can't read it. It's like 0.04%. 12% have E. So if I tell you it has an E in it, I'm not telling you much information. I'm not relieving your uncertainty. I'm not decreasing it. But E, with E, I'm not doing it. But with Z, I've started to really narrow things down quite a bit. So statistically, conveys more information. The measure of information in a message is proportional to the number of possible messages. So it's kind of like you've got the whole dictionary, so on. You've got a certain limited number. Then that defines the amount of information one can receive. And it's written mathematically, and I don't want anybody to get scared. This is no big deal, okay? There's going to be a couple tiny equations. I won't give you the bad ones, but S is the information in a message, and M is the number of possible messages that one can transmit. Now, here's a question. How many words have 2 consecutive A's? 1. We have our information resolution decreased the uncertainty to almost nothing by saying there's 2 A's. So I gave you a lot of information by saying 2 consecutive A's in this. So now I should actually use my notes so I'm not surprised myself when I'm doing this. In the 1960s, it was these jokes that went around for a very short period of time. One of them is I think they were making fun of abstract art at that time. And a guy would come up and he would put a blank canvas up. And he'd say, here's my artwork. And people would say, what the hell is this? And they go, it's a polar bear in a blizzard drinking milk. Well, of course, everybody looks, oh, that's ridiculous. It's white. There's nothing here. Well, and then they'd show a black one, and they would, of course, say something like, well, this is a crow in a coal mine at midnight. And in both cases, there's no information in the art. S equals M with this equation, we have one message. You get to have white, or 1, and that's it. You put it in there, and log of 1 is 0, so there's no information. You need at least a couple of bits. Now this over here, and I didn't put it in, but you could have the 0, 1, 0, 0. Each of those could be black and white. If you try to describe this, it takes a lot more description, black, white, black. And of course, the black and white picture is going to be made up like this on, say, your television screen. There's a lot of information there. And here is Jackson Pollock, and on the bottom I have a black and white version on the left. And the thing to keep in mind here is there's lots of information in this Jackson Pollock. If you were going to sit down and describe what that is, you would have to have a bunch of those 1s and 0s and go through and so on. Now, if you have the actual color one, which is on the right, you have to add color to it. So that's more information. So you need more bits to describe just each of the segments that you may have chopped this up into, and the color. And in nature, mammals, most of them cannot see color. You go out for deer hunting and everybody has big orange things on. The deer don't see you. So the thing to keep in mind is, we ended up evolving something like this, and then we ended up over on something more like that. And the other thing is night vision versus day vision. At night, we tend to see black and white. So this is just showing that we've evolved extra information to grab. But as Claude Shannon said, content is irrelevant. I can't tell you what that is. Can you? There it is. But it is information, which is a general concept. Now, there's a certain importance to the current situation. Here's out of Scientific American in October. They talk about some of these statistical methods that are being used to decide, is a hypothesis worth looking at or not? And in there, they talk about the amount of surprisal, once again. So you can look at this, and they point out that if you look at the p-value of most of these biological and statistical things, they want a 0.05, but that's only 4.3 bits of information separating you from nothing. Remember how many bits are in a single English word? Does that look like a really good amount of bits to say you have some sort of hypothesis that's meaningful? And here's a kind of a metaphor. If you have a flat paper as the control group, and it's flat, all you have to describe is it's 0, 0, 0, 0, 0, 0, 0, 0. There's no surprise. There's almost no, the information content's very little. That's kind of your null hypothesis. And how much, when you do your measurements, changes with respect to that. It's like crumpling the paper a bit. And you can say, aha, there's crumple here, and it's, I look at the information, oh my goodness, I have 30 bits. That's pretty good. 4? In fact, the calculations here indicate that using this, about 1 out of 4 papers of this sort are probably just wrong. And the other thing which Lee pointed out to me, Lee Shapiro, is that there are people that are talking these days a little bit about the determination of correlation versus causality. Could be whether an information transfer takes place, or it could be, and that to me is the first time I've ever heard anyone in the philosophy of science have some sort of an argument of how to get out of the correlation causality problem at all. So this is a very contemporary concern. Now, here is Rene Magritte's Treachery of Images. And when this came out, it annoyed a lot of people because it says this is not a pipe. Well, it's not a pipe. It's a bunch of small pieces of material that reflect certain electromagnetic light in different type, a different spectrum, and you look at it, and if I was going to, the information in that is devoid of any content, any meaning. You can't put tobacco in that and smoke it. You cannot do anything. Your brain is looking at that, and it is matching it up with something. It's interpreting the information and deciding, that's something, but it's not really a pipe. And I stole this off of a website, and I tried to steal it better, but what Shannon originally, this is the sort of thing engineers are taught. You have something you want to create, sound, sight, taste, touch, smell in your brain. It goes in, it's coded and turned into a transmission. It's sent along a line, so that could be like a television transmitter. And then you turn it into bits, and you add noise. And what's interesting about this is that that if you look at the mathematics of this, they all blow up unless you have noise. It's as if the world has to be imperfect for Shannon's mathematics to work decently. You get to the receiver, and it recreates exactly what the information, and it goes to your mind. But, or I'm kind of conjecturing here. I know what happens, in a real communication system. And so most of what I look at in this situation is, for the longest time, I just see this as engineering. I don't see it as any deep, meaningful thing for the universe that, tells you something important like Einstein did. And here is Lee recommended this nice book about information theory, and that's the one, if you want to read the really hairy details, you can find out how everything gets nice when you put noise in a system like this. Now, here's where it is very, somehow we evolved a thing to know coding and syntax of language, and we have this other area that interprets it. So you don't have, if you have a nonsense sentence, it knows, the Broca part knows that's a bad idea, and the Wernicke part interprets it. But whenever this is damaged, people begin to have a hard time developing what things actually mean. Now, let's talk a little bit more about information content. And I hope I'm not beating this to death too much. This is out of Wikipedia. But if you have a pair of coins like this, and you have 4 different possibilities of the 2 bits, and these, I don't know what in the world, if that's a, deer on the front and on the back is a wheel or what it is. But the thing is that I can send that information, and I can send that information to anybody, but it doesn't necessarily mean anything until I know that my significant other says, oh, I'm going to leave this coins on the table in the morning, and when you get up, if there are 2 heads like that of the deer, then you're going to get milk. And if you go, the other one there is you get milk and bread, and then the other one is get 2 milks and 2 breads, and then the bottom one is, I don't know, I'm not talking to you this morning or something, And so what you see there is with two, if you do the calculation, there's 2 bits of information there. But once again, the information is meaningless until you put a content on it, until you know that there's something tied to it. It's a general concept. Let's see. Yeah, there's 4. Let's see. Yeah, 2 bits of information. Shannon figured out how to determine the channel capacity, the number of conversations, how many bits you can cram into a communication channel. And for those of you that are old enough to remember modems, that, or they called them acoustic couplers before they called them modems at that point, and you'd see they'd started out 300 baud and then 10,000 baud, and they were getting up to like 50,000 baud, 56K modems, you remember. And I asked other guys that were engineers, that said, hey, when's this stopping? Is Shannon real? And they go, oh yeah, this is stopping. And that was the whole thing. He was the one that realized the limit. And once again, this is just an engineering question. How could this possibly have any deep meaning for the universe? And that was my attitude whenever I heard anybody talk about it. So it's just electrical engineering. All we're doing is providing you with pretty pictures of cats and videos, and that's really no other meaning for what we do. Well, some other people realized that, thermodynamic entropy and information theory, the mathematics are the same, but with a sign difference in the equations. So if you have ice, that's all nicely frozen, and like the flat sheet of paper, which is a whole bunch of zeros, you stack them up, and you have a lattice, and you can predict almost with one little thing what the rest of it is. Very little information. There's no surprise there, unless it's not epitaxial and they start. But when you get a liquid, it's all over the place, and you have to have a lot more information to describe that liquid. And when it turns into a gas, even more so. Well, engineer in me says, yeah, but a lot of mathematics span separate systems. I mean, when you learn engineering, you get mathematics that describes a circuit resonating, or a vibration of a tractor, or, so what? That's no deep meaning. So, everything's great. Let's just go back to engineering questions. This has no deep meaning. So, for instance, boss wants to know, what's the minimum amount of energy needed for a computer to operate? What is the least amount of energy needed to flip the ones and zeros in your computer to create cat videos with the most efficiency? Pretty darned engineering to me. Well, Ralph Landauer demonstrated that erasing a bit of memory increases entropy, and the associated amount of energy dissipated as heat. And at 293, it depends on the temperature. This amount of energy is about 2.8 times 10 to the minus 21 joules, and this is 2.80 zeptojoules for all the physicists who don't use it in Wikipedia. This is a very, very tiny amount. And to achieve this lower limit, the processing speed has to approach 0, though. So it's one of those fundamental limits. Now things are getting a little fuzzy. Now I've got a bit of memory versus temperature. I have an energy. It's like an equivalence of a bit and temperature. I'm getting a little more, this is kind of attaching itself a little more to physics than makes me feel better. Well, it gets worse. Because when I was in college, it was a very classical thing to talk about what was known as Maxwell's demon. And Maxwell came up with this. And he pointed out that if you have a box and it has a temperature that's the same on both sides, okay, so the temperature is the same here and here, that you can have a demon, and you can, as an engineer, you can create a little trap door that will regain its energy. It'll snap open and back, and no energy will really enter the system. And this little demon can sit there and it can look and say, there's a fast one, I'll let that one go through. And it lets the cool that says, no, I'm going to leave it shut whenever a cold one hits. And I'm going to keep doing this until one side is cold and one side is hot. Well, the minute you do that, you've got a temperature difference, and from an engineer you can go, well, I can make a steam engine now. I can sit there and I can do work out of this, and we'll run a factory, and no energy is going in from the demon, yet I'm getting energy out. So that violates conservation of energy, which most physicists like a lot. So, you know, he has to, it's a yes or no decision though. It's a 1 or a 0, it's binary. And it's equated back by Landauer to an amount of energy. So you begin to get this weird idea of, my goodness. I mean, John von Neumann said that a bit was, he wanted to put it in the metric system because he saw it as pretty real. And so you're sitting here thinking to yourself, wow, this is pretty weird. And this might be out of Wikipedia, I can't quite remember. But he has to discard or store it. And one of the things they mention is that you can get away with this until you run out of memory. And then when you begin erasing, that's when the entropy occurs. If you read other papers, they point out you have to have entropy to set these all to zeros. So you're kind of cheating, saying that you don't have to do any preparation for this. So in the end, yeah, no matter what, when you set a situation up, you're going to end up using energy for the 1s and 0s. Oh, yeah, for those of you that are interested, you might look at this video that Claude Shannon has of his little mouse, which is very kind of similar in its own way. So, okay, well, what is information? I mean, I'm sitting here talking about it. Well, the first time I encountered this was in 1988. Rudy Rucker wrote a really excellent book called Mind Tools. And I remember reading this. He said, relative to information, we are in a condition, something like the condition of the 17th century scientists regarding energy. We know there is an important concept here, a concept with many manifestations, but we do not yet know how to talk about it in exactly the right way. And I remember reading it at the time and I thought, well, that's nice. I like reading these books. And I didn't think much about it because, well, engineering, you know. Well, the best book, and thanks once again, Lee Shapiro has made this talk way good because of all the suggested books, but I read this book, Decoding the Universe, and in there he says, in 2006, he says, information theory is so powerful because information is physical. Information is not just an abstract concept, and it's not just facts or figures, dates or names. It's a concrete property of matter and energy that is quantifiable and measurable. It is every bit as real as the weight of a chunk of lead or the energy stored in an atomic warhead. And just like mass and energy, information is subject to a set of physical laws that dictate how it can behave, how information can be manipulated, transferred, duplicated, erased, or destroyed. And everything in the universe must obey the laws of information because everything in the universe is shaped by the information it contains. You'll notice I have this in a yellow box. If you forget everything else I said tonight, remember that. Because that, to me, was kind of a knockdown, and this is the best. I'm embarrassed I paid $6 for a used copy, and it's the best $6 I ever spent. It is highly mathematical, though. You should have a background like that to read it. Okay, well, let's go from cat videos to Schrodinger's cat. So most people have heard of this, and essentially Schrodinger, after talking with Einstein about exploding dynamite or some such thing, said, well, if you have a cat inside of a box, you have a radioactive source, you open a little shutter, an electron has a 50-50 chance of coming out and hitting a detector and then smashing hydrocyanic acid and killing the cat. And so what does it mean? You've got a 50-50 probability. How do you write this all up? And when you look at it, this is the famous thing where, well, we have to take a look at the experiment. We have to measure it to see what's happened. So the cat supposedly stays dead or alive for until you open the box and look at it. And of course, this is one of those paradoxes that, you know, is supposed to teach you something, make you think to, you know, what the hell does this all mean? And of course, this is the Copenhagen Interpretation. Some people really don't like experiments like this, and they like to rig them, like in this Dilbert, where Dogbert says, Merry Christmas, this gift is based on the Copenhagen Interpretation of quantum mechanics. There's a cat here that's neither dead nor alive. And Gilbert goes, well, where are the air holes? He says, I have control issues. So the thing about cats is they're big and they're warm and they radiate information. And in Decoding the Universe, he points out information and decoherence holds the answer to the paradox of Schrodinger's cat. Yes, the cat can be put in a superposition of some sort, at least in theory. But because the cat is big and warm, the information about the cat's state leaks into the environment even before someone's opened the box. The cat state decoheres in a tiny, tiny, tiny fraction of a second. The flow of information into the environment is too fast. Nature measures the cat long before anyone can open the box. So, yes. Well, okay, we're still kind of talking about information, and this is where, when I was, wandering around aimlessly as an engineer, where I started seeing this, and it just seemed absurd to me, where Kip Thorne and Stephen Hawking had an argument with John Preskill about information going into black holes. You've probably heard of this sort of thing. And Thorne and Hawking said that since general relativity made it impossible for black holes to radiate and lose information, the mass energy caused by Hawking radiation, which is this area outside where things jiggle and there's always particles and antiparticles are made, and they can split apart, and this is theorized radiation that could come out of the hole. And they said, well, then Hawking radiation can't have any information, it has to be new, and it must not originate in because it's at the event horizon. And so they say quantum mechanics would need to be rewritten if this is true. And Preskill said, no. He said, since quantum mechanics suggests that information emitted by a black hole relates to information that fell in, so if I fell in, the information that comprises my body, even though I'd be dead, is still there. It's going to be a part of it still. And the winner said that they would receive an encyclopedia of their choice from which information can be received or retrieved at will. Well, I pulled a little bit of a fast one here. I went from good old Shannon information to quantum information theory. And if you want me to talk about that, I'm completely unqualified. But I will go ahead and quantum information, or Shannon, is a 1 or a 0. The world's a 1 or a 0, and that's just it. However, a qubit has a 0 or a 1, or it can be put into a coherent superposition just like the daft dead cat. So you can have bits that are half alive and half dead, you might say. They haven't quite decided. But you can have a superposition of both. And these guys are talking about quantum information as opposed to straightforward Shannon information. And it turns out all these different things right here have information support according to Wikipedia. I understand this one more. The polarization of light makes perfect sense to me. But all of these different things essentially are tied to quantum information. And there are guys with giant brains that have worked out all the mathematics on this. And so the thing that I was going to point out at this point is these are the things that quantum computers are supposed to be. And you have Josephson junctions down here. Quantum computers are supposed to be built out of. Well, the one thing that most engineers know damn quick is you build a quantum computer, any of these qubits that are in a superposition don't like to stay there very long if they get warm. And neither does your Schrodinger's cat because it's warm and it lots of information. So what I say about Schrodinger's cat stands. The universe measures him faster than you could ever bother looking at it. And the Decoding the Universe has this brief description. I just thought I'd go through it again. Hawking and Thorne wagered that black holes truly consume information, destroying it when it passes the event horizon. if you store a qubit on a star, say a pure 0 or 1, or a mixed 0 and 1, and that star suddenly collapses into a black hole, that qubit is lost to the universe forever. Pascal, on the other hand, gamble information is conserved. Though the qubit is lost to nature while the black hole exists, it's just trapped until the black hole explodes. When a black hole self-destructs, the event horizon disappears and the original qubit will be there somewhere. Fascinating book if you have the background to read it. It's really great. So now I'm going to talk a little bit about the influence. You've probably heard about lots of information theory in the press and so on. And the one that struck me that I heard about one day that I found interesting is entropic gravity. And think about that. The name is entropic entropy, back to information equals entropy, da-da-da. And Wikipedia says that based on string theory, black hole physics, quantum information theory, it's an emergent phenomenon that springs from quantum entanglement. And at its simplest, which I like, the theory holds that when gravity becomes vanishingly weak, levels seen only at interstellar distances, it diverges from its classically understood nature, and its strength begins to decay linearly with distance from a mass. Okay, why do we care about this at all? Well, because if you ever want to upset dark matter people, say MOND in front of them, or modified Newtonian dynamics, which is a kind of a curve fit at best to try and explain why galaxies are rotating at speeds that don't make sense and why people want to postulate dark matter and all this kind of stuff. And so what they're arguing is that if they can use entropic gravity explaining information theory in with the mix, they can explain why we're seeing these strange differences that people are trying to look at dark matter at right now to figure out. Not Wikipedia. This is me shooting off my mouth of what I think it's all about. But what you can see is information theory is kind of starting to permeate lots of science. And one of the questions, though, is, of course, I'm going to go back now to basically regular Shannon. And I'll justify that in a little bit here. But, you know, we have this information processor somehow that was somehow evolved. And how few neurons do you need to build a brain? I mean, you look at what we do, and it's absolutely astonishing. And I just ran across this while I was working, researching this. And I read that this worm only needs 300 neurons to do things like sleeping, learning, smelling, and moving. That's an astonishingly small amount. How does it do this? How is information put together and processed? How in the world did this evolve to do this? Why? It doesn't make any sense to me at all. How did a brain evolve? You know, it gathers information and codes it, sends it through a Shannon information channel, and then reconstructs and interprets it. Your eyes, your 5 senses, they all evolved Shannon. Struck me as pretty weird. I started having to take this a little more seriously. You know, how in terms of current evolutionary thought, how exactly does this happen? Well, Lee recommended I read this book, and I'll be honest, this one really kind of blew my mind. People that know me have heard about this way too much. But it's what Darwin got wrong, and it's a philosophical discussion of evolutionary theory. And in there he says, equivalently, the theory of natural selection cannot predict, explain what trait the creatures in a populations are selected for. And you're kind of saying, well, look, if I give you this landscape and I put a creature in it, what's going to happen? Can you predict that? And the answer is no. We always have a just so story afterwards. And it could be anything. I mean, you look back, why did we get color vision? You know, like the Jackson Pollock. Well, we got it because we need to find fruit. Well, that's after the fact kind of an argument. How do you set up an experiment to demonstrate that's what happened? And he said Darwin, and we suppose Gould and his name, thought that we could start with mental processes and then get to natural selection by abstracting the minds away. That one was the one that struck me philosophically, because this is like when Darwin originally said, I'm going to change pigeons. You know, these guys changed all these pigeons. Now I have an information processor up here that's doing if-then-elses, making decisions about the universe, Turing machine. Yet Darwin then says, abstracts that away, and then points to a randomness in the environment. To me, philosophically, this was just insane. I could not, I understood their point. It freaked me out, in fact. But these guys have no answer, by the way, for any of their attacks. Natural history isn't a theory of evolution, it's a bundle of evolutionary scenarios. Darwin argued that, to borrow Dennett's phrase, phenotypes carry information about the ecologies in which they are developed. And that hit me at the time, thinking about it. Information. So this is an information landscape, everything in here. And me as a person has information storage device, also DNA that stores information about the environment, reacts to it. Okay, I'm fuzzy, this is a fuzzy description, but I can see the problems with the current theory. Both of these authors are secular. They see philosophical problems, but not the scientific solution. Selection 4 led me to think a lot about information theory, which is, I hadn't thought about it, in fact, since I had been in college, learning it just to make cat videos, essentially. Then, that one, I forget what was that. That was 2010, they put this book out. 2019, Paul Davies put out a book called Demon in the Machine. And I was quite happy reading it to discover that sizes involved in biological coding appear large enough to reduce Shannon information rather than quantum information. So we still have something to talk about here. I wouldn't be qualified to even think about it. Every cell has 3 billion DNA bases. The number of possible combinations is approximately 3 followed by 600 million zeros. Compare that to the paltry number of atoms in the universe, 1 followed by about 80 zeros. One of the problems, for me, is that, and I hate saying this in this room, I hate saying it me because there are people that know me, religious people have a point about the probabilities involved. They're absolutely terrifying. And you need something to select out what's required to make evolution work. I'm not going to, point at some deity. I might point at Shannon, but he's not quite a deity. And by the way, Shannon took none of this seriously. I read his biography. He was a pure old engineer and said, physicists, stop this. We're just making cat videos. Evolutionary change is now seen as happening at lightning speed. This has all been realized in recent years as we're seeing evolution occur right in front of us at an incredible, too fast to be random, really. Let's see. And here is, of course, Davies saying, you can probably get a little bit of his idea. He says, evolution would certainly work much faster and more efficiently if nature engineered just the right mutations to help out. In a way, Lamarck envisioned. Nevertheless, biologists long ago dismissed the idea as too much like the guiding hand of God, preferring instead to appeal to random chance as the sole explanation for variation, and that's the way it was for many decades. Now, however, doubts have crept in. Levin's monster worms, that's another thing we won't go into, but it was quite compelling in here to read about, are surely a clear example of the inherence of acquired characteristics. And if you saw Lee's incredibly interesting CRISPR-Cas showing essentially Lamarckianism occurring at a coding level with information, as I see it, this makes a lot of sense. Now, it makes me suspicious a little bit, and I'll just tell you that, Davies, he's a theist. And he actually in this book does not go even remotely as far as I do, as far as my arguments go. This book, once again, this one was suggested to me by Lee, and it was one of the best I've also read. And it's called Improbable Destinies by Losos. And it's 2017, so that's a couple years before this. But this is really pretty interesting. You can see science often gets incremental because it goes a little bit it's like I can only push so far. and then it might get a little, tough. He points out that Stephen Jay Gould argues that if you rerun the evolutionary clock, you will get very different results. Losos points out that a number of species have populated separate islands and evolved in a manner that follows a consistent path. Rerun the tape of life as often as you like, and in the end, the result will much be the same. This is completely, and this is more scientific. This is arguing that you can repeat Darwinistic things. And in this book, he has a bunch of examples, and I can't recommend this enough, and anybody can read this book. He goes through a bunch of examples where they are now, researchers are doing more or less controlled experiments trying to recreate evolutionary outcomes in a way that repeat themselves.
How
Mm-hmm.
how narrowly repeated? I mean, what kind of, when you say repeat, how
Mm-hmm.
narrow is this kind of repeat? Do you get a lion like a lion, or do you get a
See,
mammal?
and here's where I'm hoping that someone else in the audience, right there, might talk about that in Darwin Day. You want to say something, Lee? Yeah. Okay. Yeah, Lee will be glad to fill you in on that one. New one, and this was it. There's a number of things. This is just a quick bunch, but you really ought to read this book. It's great. New and Old World porcupines do not share a genetic ancestor. They evolved from different unquilled rodent species. How? And how did they do it so fast? Unless there's information storage transferred and there's a counterfactual in there that tells them which way is a good idea. Repeatability of E. coli adaptation to become antibiotic resistance. It would go through a sequence of mutations that were the same. They would do it again, and it would go. So that was repeatable. Caffeine evolved separately in 3 different times in coffee, tea, and cacao plants. The chemical pathways were different for each different lineage, different evolutionary paths. And where you really start to see it is where, when Lee talks about it at the biological level, it becomes absurd to see evolution the way that it is stated these days. Well, I couldn't help myself. I tried to see if I could get Losos to come give a talk. So I emailed him, and I mentioned that I'd written up my own version on my blog. It's called Yes and No is the essay. And I go through the numbers that made me realize that information theory may be central to really understanding evolutionary theory, and not this, just so stories that we end up with. And he says, thanks for your words. I'm delighted to like my book. Your ideas in your essay are provocative, which makes sense as a follow-up to what Darwin got wrong. So he's clear, he read it also. He says, I don't know if you've picked up on how controversial their school of thought is for pro and con debate in Nature from a couple of years ago on the extended synthesis. So people that are doing this stuff are aware of these problems. They're not talking about it, loudly and out, straightforwardly. But I guess I'll go for provocative. My guess is that information transfer and interaction between the information environment that surrounds a life form. Everything around us is information. And it stores in what's in the DNA. And that was the thing that struck me to even think about this. When I was taking information theory class, one of the professors turned and said, oh, just as an offhand, he says, yeah, it's interesting. He said, do you know DNA follows Shannon coding? That to me seemed a little weird to be a coincidence. But it was one of those throwaway things. We were off making cat videos. And so it stores within its DNA. And by the way, John von Neumann talks about something very close to this years ago, which shows why he's brilliant. Interacting with the life forms are involved in kind of an information struggle. You've got the information of the creature with the stored information of the DNA and so on in the reproduction, and you've got the information pool of the world outside, which we like to call an environment. And these things interact, and it stores. The DNA stores this somehow. And they're involved in an information struggle. And they react to each one. And what they're trying to do is an attempt at incorporating the stored energy. Something eats something else. The other key postulate is that the universe has a set of limitations that were baked into the cake at the moment of the Big Bang. What I mean is that the universe is like a set of building blocks that have only a limited number of combinations and not an infinite number. Now, anything goes is limited by a Platonic set of restrictions. So you can't, nothing is evolved we know of to create energy out of nothing. And not all combinations are, they're finite. They're very, very large, but not infinite. But that still doesn't save us because the numbers are so crazy big. The final bit of information is that one definition of life, and this is what I grabbed onto, is that it reverses entropy, just like Maxwell's demon. And how does it do this? Well, if it uses information in a manner like that of Maxwell's demon, and it can reverse entropy, but it would require an input of energy as a trade-off, it uses entropy, it uses the information to figure out where to get the energy and how to reverse entropy locally to create the much more ordered structure of a human being, of a cat, of whatever, whatever life. And yeah, there's my complete essay if you're insane enough to read it. And in summary, as if you need more, my view is that information is stored using a currently unknown mechanism which allows generations of organisms to produce counterfactual information. That is, there has to be some idea that going this direction is better than going that direction. Using and changing an organism's phenotype, that is what it looks like, how it's expressed, its physical, chemical makeup, in an optimum manner as possible in response to its external information environment. Rather than Darwinian slow change, this is local biological information pool in response to the requirement that it maximally obtain energy from its external environment, because that's what it needs. It uses information phenotype selection algorithms that are much faster and produce more variation than expected by Darwin, and also change multiple aspects of an organism concurrently. Of course, the competing biological information pools will also react to the reaction. And the only thing I can do to defend myself is that Schrodinger, which I don't know if I should use mine and his name in the same sentence, but he argued for this thing called an aperiodic crystal. And later on, when DNA was discovered, Crick and Watson pointed out that in Schrodinger's essay, What is Life? Yeah, you hit it. There's this thing that has to code for information. That's a big, long molecule. I'm arguing we haven't found any of this yet, but I'm predicting I don't see it can't be there, personally. And then down at the bottom, unless you really want to see it, there is a documentary that's theoretically could come out someday called The Bit Player that's all about Claude Shannon's life. And I just have a link there to the trailer for that. So I really appreciate you listening to all of this. I hope there was something interesting for people in this. And so I guess I'm done. And if you have any questions for Lee, please do that. Thank you. Sure.
Where do you stand when you were talking about the black hole, whether it gets trapped or dies in the black hole? Do you have a position on which it goes?
I am really having a tough time with that, because one thing that's striking me is E equals mc squared was the amazing thing that Einstein came up with. He said mass and energy, they're the same damn thing. So you don't have law of conservation of energy, law of conservation, you have mass energy. When Landauer and these other guys started talking about equivalence between a bit and energy, I began thinking, well, there's a lot of people, including in Decoding the Universe, say energy can't be destroyed or created. So if I had to come down on the black hole paradox, I would say, I don't think the information can be destroyed. I think it has to stay there until the black hole explodes. But that's gut feeling. I don't have any math to say QED 2 equals 1, that can't be right. You know. So, but that's my guess. Yes.
Where are modern-day Darwin evolutionary biologists in on all this?
They're having a fight like a bunch of cats in a bag that have been thrown into a river. They aren't doing it out in the open exactly, but you could see they're all being, Mr. Polite. You can see he's saying, well, you should look at the extended synthesis. Well, a lot of guys, when you first explain this, it sounds a lot like theology. It sounds a lot like something is coming down and doing this. Well, no, and I'm not saying that either, at all. And so there's this visceral, I don't want to get off on a tangent, but if you ever watch All Watched Over by Machines of Loving Grace by Adam Curtis, he talks about what happened when ecologists suddenly realized there was no such thing as an ecosystem. They became viscerally upset. This is something, it has to exist because we've believed in it. It goes clear back into the mythology of the balance of nature. Native Americans, balance of, and when they discovered this, they became very upset. And what I'm seeing is this automatic reaction is what I'm seeing by a large number of evolutionary biologists saying, just this visceral reaction of, no, Darwin's right. What in the hell's wrong with you? Stop this. You're making a mess. And for me, it's not really, and I hope, and Lee will probably go into this, I hope, in February, it's a lousy scientific theory. It doesn't predict things. It doesn't do what other scientific theories do. It might even be as bad as economics. And so I think I sort of might have answered whatever the question was. I've managed to forget.
Could we go back to the side ask a question?
Sure.
At that point?
Oh yeah, you can preferably.
What exactly are you asking?
Well,
Just
the
like
repeatability, how narrow is this? Because you talked about it kind of repeating.
Mm-hmm.
So are we repeating to the point of my explicit question was, are we repeating back to the point of a lion or back to the point of a carnivore?
All right, I'll try to answer that in several ways. It's kind of a bit of an amorphous question, but I'll answer it in a couple of ways. The first is, let's take the diversity of life. Everybody, the people who are into evolution love to throw this phrase around. And actually, that is so wrong-headed. It's crazy. Let me give you an example. The diversity of life, people talk about, well, we have spiders and we have birds and we have mammals and all this other stuff. But here's something that's surprising. Every single organism on this planet is carbon-based, uses only one isomer of amino acids, the L form, all use nucleic acids to transfer information of any sort, uses only 20 amino acids for proteins, and the number of exceptions is precisely 0. None. In other words, look that way, say, wow, all this random stuff going on, how come life is so uniform? I'm struck by the uniformity of life, not by the diversity of life. You're looking at the problem completely the wrong way. Where are the non-carbon-based bacteria? Where are the giraffes that use D amino acids, not L amino acids? Why is it going in this direction? Whatever. So my overall point, when it comes to evolution, Randy's a lot smarter than me in terms of all the mathematics. But the first thing to notice is whatever is going on, whatever the answer is, I'm telling you what it ain't. It ain't random.
I'm not suggesting it is, but all
But-
I'm asking, when he talked about...
But these, as I said, these examples of uniformity I gave you are exceptionless. Let me give you another example. People know about, say, termites and ants. They have colonies, and they're almost identical in terms of how they're structured, right? You have soldiers, you have nurses, you have eggs. They even cultivate fungi the same. You might say, oh, well, of course they're the same, because after all, one evolved from the other, except for one problem. They're not related at all. One is wasp-derived and one is other insect-derived. And somehow, independently, no cheating, no peeking, they have evolved the same identical social structure, and each member of the society has a brain the size of half a grain of sand. This is not coming from random changes. They happen to find the same solutions. This is because there are regularities in the universe, guiding principles in the universe that make things come out the same way.
And,
This gets to your question. And the question is, what are they? The answer is, I don't know. I wish I did. But I do know that when you have guiding principles and regularities among physical objects, there is an informational component of that that's making it happen. If you don't think information is real in the universe, and I have a hard time understanding all this stuff because I'm not good at it, I can give you a simple example where it's real. For example, the speed of light is a number, right? You can measure it. You've done it 1 billion times or whatever it is. That's information. G constant, H constant, Planck's constant, all these things are information that's out there. It's not us. It was out there. It was, as Randy said, baked into the universe itself, and it's completely real. If there were no human beings on the universe, these numbers would be the same.
And to your question about the
Does that answer your
experiments.
question? Does that answer your question?
Yes,
Okay.
I think you did, and I think the answer, I mean, if I would infer the answer to the question is that you end up not necessarily with a lion, but a carnivore. I mean, the pattern, the fact that you can have ants and termites that are different possible outcomes of this set of relatively stable rules.
I forgot to mention something that while I didn't put it in here, I had too much crap to put in here the way it was. But about maybe 4 months ago, there was archaeologists discovered a really strange situation on an island. The bird, yeah. This island it's submerged. There was a bird showed up of one type, evolved to the island. The island was submerged, killed everything, came back up, same bird comes, same evolutionary outcome, 5 times.
Yeah, the bird is flightless, and what happened, it re-evolved, it didn't fly back. It was completely killed. Every one of them was the genocide. And then the exact same, basically the same animal.
Essentially the same animal evolved.
In other words, there are guiding principles. There are paths that
Well, there's
are being
intelligence in the
followed.
DNA, in a sense.
Well, you've got to get the key is, the way to describe it is, you've got to get the molecules to think for themselves. The better way to think about it is the laws of physics are doing it. That's another way. The laws of physics are another way of saying that they are rule-based by regularities in the universe. So it is planned without a plan. It's planned with a planner if you believe, if you're of a religious persuasion. See, I think it was Dawkins got this dead wrong about the watch without a watchmaker. She really missed the boat here. When you see the watch, you say, well, somebody had to do it. But if it happens life is basically like that watch. It is highly improper. It's impossible to believe that came by random chance alone. And that the watch is being made by the laws of physics, the laws of the universe, the regularities are pointing in one direction, and that's the way it goes. Another way of looking at it, life in the universe will look just like this.
Yeah,
We're the plan, and we're part of it.
and how, for me, the big question is, how did we evolve brains? What was the population pressure that created a mind, began processing information and then interpreting it in terms of because we interpret things. We look around and you throw a length of hose in front of some ducks and they'll freak out thinking it's a snake. What is the Darwinian explanation of creating a mind? That to me the more I thought about the philosophical aspects of this, the more I began to think about evolution as really circling the wagons and not answering anything. And I don't like that. I'm a scientist. I want science.
So revivalism doesn't get it done for you.
No Mr. Spencer.
Yeah.
But what does is reversal of entropy. The idea, and once again, if energy is equivalent to information, and you can use information to reverse, I can see that tie. I can see that, and that's why I had the nematode worms, I think it is, that had such a small number of neurons that could start to process. So, yeah. Uh-oh, now I'm in trouble. Yes, sir.
Further, what Lee is saying is that the science fiction writers have had it right all along, is when we do encounter intelligent alien life, we bear a lot of resemblance.
Yes, I think he's right.
In part, yes, but yet, if you watch Star Trek, which I used to do, remember the Devil in the Dark, the Horta, is silicon-based, and I'm saying that's off the table. But yeah, they're going to be a lot like us. How are they going to be like us? Well, not English.
They're going to be of a certain size.
No, they're not going to be English and have orange skin and red, whatever. They're going to be carbon-based, 20 amino acids, L-amino acids. They're going to use nucleic acid for information transfer, just like us.
Probably not going to be much larger or smaller than us. This ability to manipulate their environment.
Well, we do have dinosaurs. I don't see any, for example, could they be as big as a dinosaur?
More questions? Okay, I'll do my best.
I mean, little less questions, also comments, because I did my graduate school work on this.
Oh, I'm screwed now, huh? Okay.
And I agree with the idea of regularities, but to say that other aliens would probably be carbon-based amino acids is it's more speculation. There is no reason to.
I agree with Lee. It's not speculation. Yeah.
I mean, if I could just
Sure.
finish. Couple of things. In terms of your question on there's a very great book called The Blackhole War. It's actually this intellectual battle between Stephen Hawking and another guy called Leonard Susskind. It's a great book. It actually goes back all the way to the first time when Hawking actually talks about this information dropping into a black hole. And everyone was okay, and a bunch of these couple of guys who were oh no, all of physics is screwed now if Hawking is right. So for the next 20 to 30 years, this one question motivates these couple of guys who try and go back and forth on this. So it's a great book to and it explains a lot of these things. And in terms of information itself, there's a lot of I agree that more work is needed in terms of the way biology is explained right now. And to kind of help with that, there are more physicists interested in these kind of questions, right? Because
And let's have more than 4 bits of difference in our hypotheses.
Physicists for a long time have been interested in questions more regarding black holes and beginning of the universe and stuff like that. And it's gotten to a point where some of these things can't be tested. A lot of so there's a greater interest in physicists being interested in biology. That seems like the next frontier. And there is work that tries to in what you were saying, instead of trying to explain, you have to think of it as levels of explanation. Darwinian and natural selection works at a certain level of explanation. Physics tries to do the same thing the same process, but at a different level. And they're trying to bring in their expertise to say, okay, everything that we now describe as Darwinian evolution or whatever evolution, how do you explain that purely in terms of entropy change, purely in terms of information flows and so on? And there is starting work. It's we're literally at the beginning of this. I can point towards a bunch of papers that are very initial stage.
Oh, yes.
Couple of they can do it for a couple of atoms that kind of explain these kind of things, but we are so far away from being able to simulate that in large scale systems. It's hard. We can only make directions. And like you said, a lot of these things, part of my chapters in the end, I had to in my dissertation, I had to be this is speculation. At some point I have to say this is speculation because I can say there are indications in the laws of thermodynamics that say this has to come about, but there is no way for us to know right now. And in the sense that I expect regularities. You're right, there has to be a certain level of regularities, but I wouldn't go as far as to say that it has to be 20 amino acids or it has to be, I have no idea. There is no way for me to know.
The chemistry points to carbon. You look
Here.
at
under
is
these
there-
conditions.
Well, unless you're talking about a universe that has completely different rules.
No, I'm talking about a different kind of environment where silicon was available and the temperature conditions were different. Would that allow something else to silicon? Like, I can't rule that out, right? I can't, like, all I can say is in this kind of, like, and this also goes back to how we look for planets with possible life in it. Because we know of the one planet that does have life in it, we look for similarities, right? But if we had a different, more like a physics-based understanding, then maybe we'd start looking for a different set of planets too. So, like, though we would expect regularities, all I can say is, like, any kind of, like, presumption that I would make that it could only be carbon-based is a speculation at best. Like, even in terms of, like,
stronger than speculation. But
I mean,
yeah.
I'll push back, but, like, I'll let you give your explanation for it.
First of all, you're exactly correct that it's speculation, but I have no problem with that. I'm not going to argue with that. But there are reasonable speculations and there are unreasonable speculations. If you think the Broncos going to win the Super Bowl, that's not a reasonable speculation. Now, it is clear, I think, and most reasonable people will say there are all kinds of restrictions on life. For example, if it was anything goes, like Star Wars or Star Trek, then there'd be shopping malls on Mars, and there'd be life. It would be so easy to find. There would be television shows. There'll be, I Love Luna coming over the airwaves. But in fact, the fact we haven't found any life on any other planet, to the best of our abilities, makes you wonder that, well, okay, so we agree there are restrictions, and it also is supported by the idea that life has so many exceptionless regularities here, you begin to wonder. So the question becomes, how restricted is life? So that we begin to, we start with that. Now, as you point out, there's no way to know for sure, but now my specialty happens to be infectious diseases. And a hot area besides the microbiome, which somebody did a very nice talk on, the other one is extremophiles. Oh, these are bacteria that live way up on mountaintops and miles under the sea and in thermal vents under conditions of extremely high or low pressure, extremely high or low temperature, extremely high or low radiation levels, and yet they are all the same. In other words, when I think of a thermal vent, I'm thinking of Pluto. When I see a mountaintop, I'm thinking of Jupiter. When I see radiodurans bacteria, I'm thinking of what would it be like to live on Mercury. Despite all these extreme environments, these regularities exist. There's no, in other words, evolution, biology can't change significantly to fill these niches in a way that's different from what we have here. So you're right, I'm speculating. But when I see these different environments, I'm thinking of other planets. I'm not thinking of 3 miles under the ocean in a thermal vent. I'm thinking no matter how the environment changes on these other planets, I have some rationale to say, boy, I have a feeling it's going to look like us. And by us, I don't mean speaking English and, by us, I mean the kinds of things Randy's talking about. This carbon-based life is not just a random thing. Carbon can do things that silicon can't do. There are
Sample size pretty small.
Yes, but what do you mean by these conditions? You mean here, or do you mean 4 miles under the ocean in a thermal vent?
I mean, under the, 4 miles under the ocean also was not where higher level carbon-based life forms grew up either, right? Let's be honest. Like, we don't have humans being evolved 4 miles under the ocean.
No, but we have
Complexity
we have bacteria there.
But not humans.
No, I didn't say we did.
No, but I'm just
No, but I'm saying, see, when I say life, I don't mean humans. I agree with NASA. I think NASA got it right here. There are more, microbes are much more likely than I agree with that. But the microbes are going to be like our microbes. They're going to use nucleic acids, carbon-based, very similar surface structures, and all this other stuff that I think is more likely than not. Can I prove it? No. Is it speculation? Of course it's speculation.
Yep.
But when your tax money and my tax money is building a $4 billion probe to go jetting off somewhere.
Which is a good thing.
Oh, God, don't get me started. I think NASA's got it right. I think using mass spec to look for life like us is the right idea. Chemically like us, not speaking English.
And the other thing I did not mention in here
Does that make
is,
sense? Does everybody understand where I'm going with this?
I do, you're probably right. I was just saying before that I think your sample size is pretty small in terms of how many other planets we've been able to investigate, and there's 100 billion galaxies.
Right, but if it was anything goes, there should be life everywhere, right?
Well, yes, but
if it's
we see in our own example that is when the civilization gets to the point where it can destroy itself, it does. And that may be the pattern throughout the universe. And so the fact that we're not seeing all these other cultures and civilizations.
well, I like to see the nuclear craters somewhere in Pluto. That would help.
We're asserting the great folks.
Like in terms of because now it's not just about science; it's about economics too, right? If I only have a limited amount of money to spend to look for stuff, I completely agree. Go look in planets that look like ours, right? But that doesn't mean that other kinds of life forms can't exist. Because if this is purely a case of economics, if I was saying, okay, you're given 100 billion, use that wisely, I would say, okay, let's just find planets
that are similar to ours, because that's the most likely thing to, because we don't yet have a scientific framework that says definitively why they might, see, this is where the physics-based framework doesn't exist for evolution. We have a biology-based framework that explains how carbon life is evolved, and so we are bound to look for more carbon-based life forms. And given limited amount of resources, let's just keep doing that. That's completely fine. But when there's a physics-based framework that might explain why the conditions under which a silicon-based life form might come up, then I'm still not saying go look for them, but I'm saying that cannot rule them out.
and another point that I just,
The case that it's a necessary bet. I make the case that it's a good bet. That's right.
so
That's right.
one thing I wanted to mention too is, I didn't have any of it in here, but if you look up the communications between microorganisms, it's absolutely shocking how groups of them get together, how they create biofilms, how they, you're seeing information transfer and evolving right there. They're discovering over and over again there's more going on than all of them just sitting there by themselves having a good time. I think this is, like you say, where Rudy Rucker said, we just don't know how to talk about it yet, is the big problem.
I mean, I'll just end last point saying, I'll admit this, we work on this, we don't even have an agreeable definition of information.
Sure.
I
think we do, but yeah.
Yes.
Yes.
We're writing a book next year where we have multiple people, because the definitions itself are still
It's ones and zeros. That's information, the end. It's ones and zeros. No, it's not well defined. Shannon defined the hell out of it. And if you read that book, which I recommend, if you saw there, it's Information Theory and Introduction. That's the best. I wish I'd had it when I was in college. And it goes through probabilities, it shows you how these nice infinities disappear. But no, it's a yes or a no, it's a 1 or a 0. It all goes back to that, because at the very beginning, what did Shannon show? He showed 1 and 0 can represent any mathematical numerical relationships. Yeah.
That's interesting. You should hold on to that. So my question is, it sounds like what you'd like to tell us is why a quanta is not an adequate definition. And if you're not prepared to talk about that, totally okay. But I guess that's what I heard, and I'm just curious if that's the case.
Okay, so the ones and zeros, so it's like this.
Implicit in Shannon's definition of information is an external observer, right?
No.
Oh, let me use your example, right? What's the word with double A's, right?
Mm-hmm.
That only makes sense if you know what A's are.
Yeah,
To someone who doesn't speak English,
right.
double A's make no sense.
Mm-hmm.
So everything is defined with respect to an external observer. This is the thing about Shannon's information. From an outside perspective, it looks very simple. Zeros and ones, it's very intuitive. But once you get into the weeds of it, this is an active area of research where people argue about nothing about Shannon information, right, makes sense in terms of information if you don't have someone external to it. Because nothing about information in English makes absolutely any sense to anyone. You could have a book in English, right?
So this to me is not a profound statement. This is, to me, Shannon is general. It's a general concept, the same way the Pythagorean theorem is a general concept. You're saying, well, if you're going to use the Pythagorean theorem, you have to decide, am I modeling planets? Am I looking at a waveguide and checking out the dielectric? Yeah, but the Shannon itself, the mathematics itself, is well defined. And yes, you have to figure out how to talk about your biological systems in terms of Shannon. But Shannon does not need anything else. Lee?
Can I make an analogy? And I think it's right. I'm not an information person, but this may help. Information theory, as described here by Randy, is more like is syntax, not semantics. If I say if A equals B, if I say if A equals B and B equals C, then A equals C, it doesn't matter what A, B, and C are. You can interpret them any way you want, but the law still holds. So when Randy's talking, I think where he's going with this is when you have information, it doesn't tell you what information is being transferred. He's telling you what the quantities are that you can squeeze
And
into
what
this
it means.
thing. Whether the information you're using is telephone numbers or pictures of cats or anything else, that's called the interpretation on top of, that's the semantics on top of the syntax. Pure theory is syntax only.
That's precisely it. The information is there.
The syntax
Is that
never
a
changes.
pipe or is it not a pipe? You know?
I mean,
You know,
this is going to go into a very
Yeah.
long argument.
Sure, no.
I
It's
don't want to like hijack
yeah.
this, so I'm just gonna like.
okay.
Are there other questions?
Well,
Is there somebody,
Any other questions?
any other questions? Okay, let's thank our speaker again.
Thank you. Worth the admission? Price?